In a couple of videos, we've talked about reaction energy diagrams. In this video, I just want to give some more details. So it's important to remember that kinetics and thermodynamics are different concepts. Thermodynamics tells me about which direction a reaction will go, but the kinetics tell me about how fast a reaction will be, and they're not necessarily connected. We can have spontaneous reactions. That means that they're product favored and they go to the right. They can be very fast, and we can also have spontaneous reactions that are very slow. But the reaction energy diagrams actually has information about both the kinetics and the thermodynamics of a chemical reaction. And when we're thinking about kinetics, it's primarily about the activation energy that we're interested in, right? So it's the difference in energy between the reactants and the top of the barrier in the reaction energy diagram. Whereas the thermodynamics, we're thinking primarily about the difference in energy between the reactants and the products. And so for thermodynamics, we don't really care about what happens in between. We just want to know what the relative stabilities of our reactants and products are. So to think more about the difference between kinetics and thermodynamics, let's think about the hypothetical reaction between the reactants A and B. And in this hypothetical system, there are two possible ways in which A and B can react. They can follow this pathway to form the products E and F, or they can react via this pathway to form the products C and D. Now, if I'm thinking about the kinetics, so how fast will each of these competing reactions occur, I'm looking at the activation energies. And so the activation energy to form C and D is lower than the activation energy to form E and F. And so the blue reaction is going to happen faster than the E and F reaction. And so we would say that the products C and D are kinetically favored because they'll be formed faster than E and F. Now for this particular reaction, it is also true that C and D are lower in energy than E and F. And so the delta G for this reaction is going to be more negative for the blue curve than for the red curve. And so C and D are actually thermodynamically favored above E and F as well because they're more stable than E and F, right? So for thermodynamic stability, I'm looking at the difference between where the reactant started and where the products end up, right? The lower the products are, the more stable they are, and so the more favorable that will be thermodynamically. But we could just as easily have a different reaction where that was not the case. In the previous reaction, the products C and D were favored by both kinetics, that would be formed faster, and thermodynamically, they were more stable. But in this alternate hypothetical reaction, we would come to a different conclusion. And again, the reaction energy diagram tells us about how this is going to occur. So for this reaction, C and D are still lower in energy than E and F. And so C and D are still thermodynamically favored over E and F. But now, in this example, the activation energy for the formation of E and F is lower than the activation energy for the formation of C and D, and so we'll actually form E and F faster. And so, in this case, E and F is kinetically favored, right? But C and D are thermodynamically favored. And so we can control our reaction to either favor C and D or E and F. So another important concept about reaction energy diagrams is the idea of transition states. So the transition state occurs at the height, at the very top of the energy barrier. And this represents the transition from the breaking of bonds to the making of new bonds. And so for this reaction, essentially we're replacing the bromine with the chlorine. And so we need to form a new bond between the carbon and the chlorine, and we need to break the bond between the bromine and the carbon. Now, transition states are called fleeting, right? They don't last for any length of time, right? Essentially, the reaction passes through the transition state, but it's not like it stays at the transition state for any given amount of time. And yet, the structure of the transition state still can tell us quite a bit about the chemical reaction. Now, an intermediate, on the other hand, is a species that's formed during the course of a reaction. They appear as local minima on the reaction energy diagram, and they actually are observable. So they can last for long periods of time, or short periods of time, depending on the chemical reaction, but they are actual chemical species that do exist. They just react further. There's sort of a stopping point on the way to the eventual products. And another thing to notice about reaction energy diagrams, and I mentioned this in the kinetics video as well, the number of barriers in the reaction energy diagram tells me about how many steps there are in the reaction. So because I see 2 barriers to get from the reactants to the products, that tells me that this is a 2-step mechanism. So the last thing I want to talk about in this video is called the Hammond Postulate. And this is a very useful tool that can give us information about the structure of transition states. And the reason this is useful is because transition states are just structures that the molecule passes through during the course of a reaction, and they're very difficult or impossible to isolate. They can be very difficult to characterize. But the Hammond Postulate is based on the fact that points that are close together on a reaction energy diagram should be similar in structure. And so the Hammond Postulate allows us to make predictions about what the transition state should look like for a particular reaction. In the case of an exothermic reaction, the transition state is closer to the reactants than it is to the products. Therefore, we would expect the transition state to more closely resemble the reactants than it does the products. Conversely, in an endothermic reaction, the transition state is closer in energy to the products. And so for an endothermic process, we would expect the transition state to be more similar in structure to the products than it is to the reactants.